Welcome to homework.
We're asked to prove that a of n plus 1 is greater than a of mn, where m and n are non-negative integers, and a is the Ackermann function. So recall that the Ackermann function a of mn is defined by 2n if m equals 0, 0 if m equals 1 and n equals 0. Sorry, if m is greater than or equal to 1 and n equals 0. 2 if m is greater than or equal to 1 and n equals 1, and a of m minus 1, a of m n minus 1, if m is greater than or equal to 1 and n is greater than or equal to 2. So to prove this statement, we're going to have to use induction. Excuse me. Let Pn be the statement. A of m n plus 1 is greater than a of m n for all non-negative integers m, and for the base case we have n equals 0 first. In this case we have that a of m1 is equal to, well, in this case this is going to be 2, which is greater than 0, which is equal to a of m0. So it checks out here. And now for another base case, we have if n is equal to 1, then a of m1 plus 1 is 2, is going to be equal to, by the recursive definition, well, it kind of actually depends on what m is. But really, this is equal to a of m minus 1. Well, I guess I'll break this up into cases. So if m is equal to 0, then it follows that this is going to be 2 times n, which is 2 times 2, which is 4, if m is equal to 0. And then this is going to be a of m minus 1 a of Actually recall that earlier we proved a statement saying that for m greater than or equal to 1, we have that a of m2 is equal to 4. And so it follows that in general, this is just equal to 4, which is going to be greater than two, which is equal to a of m1. So this statement also checks out. So we've proven the base case. Now for the inductive step. Suppose that pk is true. For some k greater than or equal to 1, then we have that this implies that a of m k plus 1 is greater than a of mk for all m greater than or equal to 0. So we need to prove that p of k plus 1 is true. So to prove that statement, we're going to let m be some non-negative integer. Then we have that a of m and then k plus 2 is going to be equal to, by the recursive definition, a of m minus 1, and this is going to be valid because as long as m is not equal to 0. All right, so break this up into two cases, really. If m equals 0, then we have that a of m k plus 2 is going to be a of 0 k plus 2, which by definition is 2 times k plus 2, which is clearly greater than 2 times k plus 1, which is equal to a of 0 k plus 1. So it works out in that case. Now, if m is greater than or equal to 1, then we have that a of m k plus 2 by the recursive definition is going to be a of m minus 1, a of m k plus 1, and recall that by the inductive hypothesis we have a of m k plus 1 is greater than a of mk, and so since this is an increasing function, this is going to be greater than, it's an increasing sequence I should say, a of m minus 1, and this is greater than a of m k, and this is equal to, by the recursive definition, or I guess you can write it just equivalently as a of m minus 1, a of m k plus 1 minus 1. So this way it's easier to see that this is equivalent to a of m k plus 1, which is what we wanted to show. So it follows that the statement p k plus 1 is true, and therefore, by the principle of mathematical induction, it follows that Pn is true for all positive integers n, which really means that a of m n plus 1 is strictly greater than a of m n for all non-negative integers m and for all non-negative integers n.